Swayam Prabha. Digital India. Educated India.
Hi everyone. In the last few classes, we have described about properties of the adjoint of an operator and some properties of closed range operators. So today we are going to define a few special classes of operators which are defined by the adjoint of an operator. So let us start with a bounded operator. Let T is in B of H, where H is Hilbert space. Then we say that T is said to be normal if T star T equal to T star. T is said to be self-adjoint if T star equal to T. T is said to be unitary if T star T equal to T star is identity operator I. T is said to be positive if inner product of Tx with x is positive for every x in H, and anti-self-adjoint if T star equal to minus T. We can easily observe that self-adjoint implies normal, and unitary also implies normal, and anti-self-adjoint implies that it is normal. So these three classes of operators are included in normal operators. Now we want to ask what will happen if T is positive. Can we say that one of the remaining classes, it belongs to the remaining classes? So we will show that when T is positive, then it is automatically self-adjoint. Theorem. Let T be a bounded operator. Then the following are equivalent. The first one is T is self-adjoint. Second one is inner product Tx with y equal to inner product x with Ty for every xy in H. And the third one is inner product of Tx with x is real number for every x in H. So these are the characterization of self-adjoint operators. Let us try to look at the proof. So 1 implies 2 is clear. When we write equation of the adjoint and write T equal to T star, then we get 2. Now 2 implies 3 is also clear because when you take y equal to x, inner product tx with x is inner product x with tx. So that says that inner product tx with x is real number. So these are clear. Now 2 implies 1 is also clear, because if inner product tx with y equal to inner product x with ty, so from that we can conclude that t equal to t star. Now we want to show that 3 implies 2. To show this, we use an application of the polarization identity. For operators. So it says that let A be a bounded operator on H. Then we can say that 2 times inner product A plus A star x with y is nothing but inner product of A of x plus y with x plus y minus inner product A of x minus y inner product with x minus y plus I times inner product of A of x plus iy with x plus iy minus I times inner product A of x minus iy with x minus iy. So this can be easily verified. This is a computation. Now in particular, if t equal to t star in our case, then we can say that 2, so t equal to t star implies that left hand side 2 into 2 times t, that is 4 inner product tx with y is inner product t of x plus y minus t of x minus y inner product with x minus y plus I times t of x plus iy minus I times inner product of t of x minus y. Now from this we can conclude that inner product tx with y equal to inner product x with ty. Okay, so from this 3 implies 2 follows. So that is a easy verification. Okay, now let us look at the equivalent statements again. So the third statement says something about the self-adjoint operator, that is inner product tx with x is in R. Now we have defined a positive operator in terms of inner product tx with x. So if t is positive, then inner product tx with x is positive, hence it is self-adjoint. If t is positive, then t is self-adjoint. Okay. Here we describe the relation between the earlier classes of operators that we have already discussed. So here the smallest is the set of all positive operators, and positive operators are included in the set of all self-adjoint operators. And this class is included again in set of all normal operators. And the unitary operators are included in normal operators, and they also contain self-adjoint as well as positive operators. Let us look at a few examples to understand these concepts. Let us start with a complex number C. Define T to be C times identity on Hilbert space. Then we can check that T star is nothing but C bar times identity. We know that I star is I. Hence we can say that T is self-adjoint if and only if C is a real number. T is always normal. T is positive if and only if C is a positive number, and T is unitary if and only if mod C equal to 1. So this can be verified very easily because T star is C bar times identity. Now using the definition we can easily get. So still we can generalize this example. Let us look at a bounded sequence of real numbers. So define T from L2 into L2 by T of xn, the sequence xn is the sequence lambda n xn for every xn in L2. That means x1, x2, x3 so on. This is mapped to lambda 1 x1, lambda 2 x2, lambda 3 x3 so on. We have observed that the matrix of this is with respect to the standard orthogonal basis is the diagonal matrix with diagonal entries lambda 1, lambda 2, lambda 3 so on. So with respect to the standard orthogonal basis. Okay. Now we want to see under what condition T is self-adjoint, T is positive, T is normal and unitary. So we can easily check that by looking at the earlier example. We can easily show that T is always normal. T is self-adjoint if and only each lambda I equal to lambda bar I for every lambda I equal to lambda I bar for every I in n. T is positive if and only if lambda I is positive for every I in n, and T is unitary if and only if mod lambda I equal to 1 for every I in n. So these properties can be checked very easily from the example 1. Now the adjoint of T, that is the matrix of T star, is nothing but the infinite diagonal matrix with diagonal entries lambda 1 bar, lambda 2 bar, lambda 3 bar so on. Now from that we can actually conclude all these results. Let us try to look at slight generalization of this result. Let phi is a continuous function defined on AB taking values in C. So we have the multiplication operator m phi from L to AB into L to AB by m phi at f is phi multiplied by f for every f in L to AB. So we know that we have already proved that m phi star is nothing but m phi bar. So from this we can conclude that m phi is self-adjoint. So we can say that m phi is self-adjoint if and only if phi equal to phi bar. That means phi is real valued. M phi is always normal. because phi bar commutes with phi. So m phi is positive if and only if phi is positive. And m phi is unitary if and only mod phi of t equal to 1 for all t in AB. This can be proved very easily. Here we are taking phi to be a continuous function, but if we take phi to be L infinity AB, phi is in L infinity AB. So let us take phi is in L infinity AB and look at the multiplication operator induced by phi. Then m phi is self-adjoint if and only if phi equal to phi bar almost everywhere with respect to the Lebesgue measure. Similarly, we can state all the other statements. That means phi is positive. Whenever phi is positive almost everywhere, we can say that m phi is positive, and so m phi is positive if and only m phi is always normal and m phi is unitary if and only mod phi of t equal to 1 for almost all t. Okay, so this is a generalization of the earlier operator defined on the sequence space. Now let us look at one more example. So we have defined the Fredholm integral operator. So let k is a two variable function. So define k from L to AB into L to AB by kf at S is integral a to b k of st ft dt for every f in L to AB. We have already shown that k star f at S is the integral operator given by the kernel k of ts bar ft dt. Now we can conclude that k is self-adjoint if and only if k of st equal to k of ts bar. Now k is small k, the two variable function is L to AB. So when we say two functions are equal, they are equal almost everywhere for almost all. Such a kernel we call a symmetric kernel that will give self-adjoint operator. Now you can easily check that under what conditions k become unitary, k is normal, and k is positive. Next we define a set depending on the operator t. So let us start with a bounded operator t in B of h and define omega t as set of all inner product tx with x, where x is coming from the unit sphere of h. So this set is known as the numerical range of t. And omega t is supremum of mod lambda in the numerical range, and this can be expressed as supremum of modulus of inner product Tx with x, where x is coming from the unit sphere. So this quantity is known as the numerical radius of T. The numerical range of an operator gives very good information about the operator, and we will see the properties of numerical ranges at a later stage. But we will connect the properties of self-adjoint operators and the numerical range in the next coming results. And in terms of numerical range, we can say that T is self-adjoint if and only the numerical range is subset of R, because we have already shown that T is self-adjoint if and only if inner product Tx with x is a real number for every x. And we can say that T is positive if and only if the numerical range of T is contained in 0 infinity. Okay. Now we can easily see that omega T is always dominated by the norm of T. So since inner product Tx with x, this is less than or equal to norm T, norm x square by the Cauchy square inequality, by the Cauchy square Bunyakovsky inequality. So this implies the numerical radius is always less than or equal to norm T. This is for a general operator. Okay, now what can we say about the other way inequality? What can we say about norm of T and omega of T in the other way? That means we know that omega T is less than or equal to norm T. Can we say the other way inequality is true? In general, that is not true, but we can easily check that. We can easily show norm of T is less than 2 times omega of T. And the second one is T going to omega T is a norm on B of H. It satisfies all the axioms of the norm. So let us see why. Let us see with an example that numerical range need not be equal to norm of the operator. So define T from C2 into C2 by T of x1 x2 as x2 comma 0 for every x1 x2 in C2. So we can show that the matrix of T with respect to the standard orthogonal basis of C2 is given by 0 1 0 0. So this is an nilpotent matrix. We show that the numerical radius of T is less than or equal to 2, and the norm of T we can easily show that by looking at T star T. So this is 0 1 0 0 0 1 0 0. So you will get as 0 0 0 1. Hence norm of T square is norm of T star T, and you know that for a diagonal matrix, the norm of the operator is supreme of the modulus of the diagonal entries. Here it is 1. So we can say that norm of T is 1, and we show that the numerical radius is less than or equal to 2. In fact, we can show that numerical radius is also 2. So let us look at let us take x equal to x1 x2 with Euclidean norm of x is 1. Then we have we have inner product of tx with x. If you look at this, is tx is nothing but x2 comma 0, so x2 comma 0, and inner product with x1 x2, so this is nothing but x1 x2. So from this we can say that modulus of inner product tx with x is nothing but modulus of x1 x2, and this is less than or equal to mod x1 square plus mod x2 square by 2. We know that norm of x is 1, so that means this is 1 by 2. So from this we can conclude that the numerical radius is less than or equal to 1 by 2 by taking supreme on the left hand side, because over now x equal to 1. On the right hand side it's a fixed quantity, so we can conclude that numerical range of t is less than or equal to 1 by 2, whereas norm of t is exactly 1. So the conclusion is that therefore numerical range of t is strictly less than norm of t in this case. Now we can ask the question, are there any operators where the numerical range and norm of the operators are same? So in fact we can prove this for any self-adjoint operator theorem. Let T be a self-adjoint operator, then we can say that norm of T, that is numerical range, it is nothing but supremum over inner product modulus of inner product Tx with x, where x is coming from the unit sphere. Okay. So let us try to look at the proof. So we know that numerical range anyway less than or equal to norm t, that we have already observed. Now we want to show the other way. So let us take vectors xy from the Hilbert space H, then consider inner product T of x plus y with x plus y. This is inner product Tx with x plus inner product Tx with y plus inner product Ty with x plus inner product Ty with y. Now this is inner product Tx with x plus, so the second component, this is inner product Ty with x, so you can take t to the other side. Since t is self-adjoint, t equal to t star, so this will be inner product y with t star x, but t star equal to t, so we can say that inner product y with tx. So tx with y plus inner product y with tx plus inner product ty with y. So this is inner product tx with x plus 2 real part of inner product tx with y plus inner product ty with y. So let us call this equation 1. Now in place of x plus y, if you look at if you take consider x minus y, so we can say that inner product of t of x minus y with x minus y, we can say that it is inner product tx with x. For tx x and inner product ty with y, we get positive terms, remaining are negative, so this we can get as minus 2 real part of inner product tx with y plus inner product ty with y. So call this equation as 2. Now from 1 and 2, we can say that if you subtract equation 2 from 1, so we can get, so from from 1 and 2, So we get that 4 times real part of inner product Tx with y is nothing but you will get T of x plus y, inner product of T of x plus y with x plus y minus inner product of Tx minus y with x minus y. Okay, now this is less than or equal to, if you take the modulus of this is modulus of inner product T of x plus y plus modulus of inner product T of x minus y with x minus y by the triangle inequality. But this is nothing but, by definition, this is omega of t norm x plus y square, and here also omega t multiplied by norm x minus y square. Okay, so let us look at this is inequality 3. So here we use the fact that inner product Tz with z modulus is less than or equal to omega of t norm z square, or inner product z with z. Okay, now left hand side we have a real number, whereas right hand side we got a quantity which is positive. Now we want to write left hand side also, we want to write that as a positive quantity. So replace, so let us take, so write Txy is a complex number, so we can use the polar decomposition as inner product Tx with y as modulus of inner product Tx with y multiplied by e power I theta. So that means you will get modulus inner product Tx with y as e power minus I theta multiplied by inner product Tx with y. So we can say this is inner product T of x e power minus I theta y. Okay, so if you replace x by x e power minus I theta, then we can write inner product Tx with y as modulus of inner product Tx with y. So now if you replace x by x e power minus I theta in 3, replace in 3, we get 4 times. So we get, instead of real part you will get modulus of inner product Tx with y, so real part of that is again the same. You will get 4 modulus inner product Tx with y is less than omega of t x e power minus I theta plus y square plus x e power minus I theta minus y square. So observe that norm of x and norm of x e power minus I theta are same, and we can actually get the same this inequality whatever we have written here. Okay. Now this is nothing but omega t, and by the polarization identity this is 2 times norm x square plus norm y square. So that means you will get modulus of inner product Tx with y is nothing but it is less than or equal to 2 omega t norm x square plus norm y square. Now we know that supremum of modulus of inner product Tx with y, where x norm x equal to 1, norm y equal to 1, that will give norm of t. So taking supremum norm x equal to 1 and norm y equal to 1. So we get left hand side is nothing but norm of t less than, so here 2 is there, yeah, 1 second. So here, so 2 times, so this get cancelled. We can say that norm of t to norm t is less than omega t, and norm x equal to 1, norm y equal to 1, so this implies norm t is less than or equal to omega t. But we know the other inequality earlier, so therefore we can say that norm t and omega t are same. So we assume that t is self-adjoint. So the fact that t is self-adjoint is used at this place. Okay. So for a self-adjoint operator, we have shown that the numerical radius and norm of the operator are the same. Now we can ask the question: can we get this equality for a bigger class of operators? For example, every self-adjoint operator is normal. Can we say that the same is true for normal operators also? Question: is it true that if t is normal, then omega t and norm t are same? Okay, so this will be looking at a later stage. In fact, the answer is positive in this case also. Okay. Okay, this is about self-adjoint operators. The advantage of this formula, whatever we proved, is that, see, if you want to look at norm of the operator for a general operator, you have to look at supremum of modulus of inner product x with y, where x and y are coming from the unit sphere. But in this case, we don't need to look at modulus of the inner product tx with y. It is enough to look at inner product tx with x. So this way, we don't have to look at all the vectors, all possible x and y. It is enough to look at y equal to x and get the formula in an easy way. And in fact, most of the times, because of this formula, finding the norm becomes very easy. Okay. Next, we want to look at some relation between self-adjoint operators. Suppose we have two self-adjoint operators, right? S and T are two self-adjoint operators. Then we can easily show that S plus T is self-adjoint, and alpha S is self-adjoint if alpha is a real number. That means if you collect all the self-adjoint operators in B of H, that forms a real vectors. So the conclusion is, so the set of all self-adjoint operators forms a real vector space but not a complex vector space. You can always find sum of two. If you take alpha equal to the imaginary I, where I square equal to 1, then it is not self-adjoint, it is anti-self-adjoint. Okay. Now let us look at two self-adjoint operators, S and T. So then we can actually, we don't know how to compare S and T, but we know inner product Sx with x, this is a real number, and inner product tx with x is also real number. So we can say that we can compare, because these two are real numbers. We can, by the law of trichotomy, we can say that these two real numbers are comparable. That means inner product sx with sx less than or equal to inner product tx with x, or the other way, are equal. So if this happens, inner product sx with x less than or equal to inner product tx with x for every x in h, then we say that s is less than or equal to t. So in other words, numerical range of s is contained in numerical range of t. Then we say that s is less than or equal to t. So if t is bigger than 0, that means when you take s equal to 0, then inner product tx with x is always bigger than 0 for every x. That means t must be positive. So when t is positive, we denote it by saying that t is bigger than or equal to the 0 operator. So notation is the following: t is positive is denoted by So next we discuss one important property of positive operators, which is called the Cauchy-Schwarz inequality. So, let t be a bounded operator, be positive, then we can say that modulus of inner product tx with y square less than or equal to inner product tx with x multiplied by inner product ty with y for every x by h. Now if you take t equal to the identity operator, we get the usual Cauchy-Schwarz inequality. So t equal to identity I, so that means this Cauchy-Schwarz inequality or CSB inequality is more general than the Cauchy-Schwarz inequality that we have studied earlier. Okay, now surprisingly, the proofs comes from the usual Cauchy-Schwarz inequality. So let us define a two variable function like this: box xy as inner product tx with y. Now tx is an element of h, y is also element of h. Now this is the inner product in h for every xy in h. Now since t is positive and since t is linear, we can show that this new two variable function is linear in the first variable, and since t is positive, we can show that this is a positive semi-definite, and we can show that this new two variable function is a semi-inner product. So check that is a semi-inner product on H. Now apply the Cauchy-Schwarz inequality for this semi-inner product by the CSB inequality. So we get that this is less than or equal to xx multiplied by yy. So if you replace this box xy by inner product Tx with y, we get the conclusion. Okay, so this is the Cauchy-Squarge inequality for positive operators. This result will be using at a later stage. So we define one more particular class of operators in set of all positive operators. So definition, let T be positive, then T is said to be strictly positive if inner product Tx is strictly positive for all x in H but x non-zero. So for all x non-zero vectors, if the inner product Tx with x is strictly positive, we can conclude that we can say that T is a strictly positive operator. So we can say that whenever T is strictly positive, the operator is invertible. If T is strictly positive, then T inverse exists and it's a bounded operator. So check that if T is strictly positive, then there exists some positive number such that T is bigger than or equal to m times identity. Okay. So one more important information, if T is self-adjoint, so we know that norm T is supremo mod inner product Tx with x, where x is coming from the unit sphere, right? Now that means we can say that from this we can say minus T norm x square is less than norm so inner product Tx with x less than norm T, because norm T is bigger than inner product Tx with x when norm x is 1. Now when x is non-zero, you replace x by norm x. So when x is non-zero, replace x by norm x to get that modulus of inner product Tx with x less than norm T into norm x square. So that's what I have written here. Now from this we can conclude that so the conclusion is the following, that norm T times identity less than or equal to T, that is less than or equal to norm T times identity. So this is true when T is self-adjoint operator. In general, we cannot compare two operators unless those two operators are self-adjoint. So this is one of the important observation. And some more observation are the following. If P is a polynomial, with real coefficients, and T is a self-adjoint operator, then we can conclude that P of t is self-adjoint. Now we know how to define P of t, because so if P of z is a0 plus a1z, so on an z power n, these a's are real numbers, then P of t a0 identity plus a1 of t, so on an t power n. We know that when t is self-adjoint, t square is also self-adjoint. In fact, t square become positive, and we can conclude that P of t is a self-adjoint operator. So if t is self-adjoint, this implies t square is always positive. And one more simple observation is that if s and t are positive, then we can say that s plus t is always positive. This directly follows from the definition of positiveness, and alpha s is always positive for every alpha bigger than 0. So from these two observations, we can say that this set of all positive operators forms a positive cone in B of h. Positive cone means the sum should, so sum of two positive operators is positive, and whenever we multiply positive operator with positive constant, that should be positive. In fact, whatever we have done for self-adjoint also, if P is a real polynomial with positive coefficients, then P of when t is positive, then we can conclude that P of t is also positive. So these are some of the important properties of self-adjoint as well as positive operators. So we'll discuss a few more important properties for normal and unitary operators in the coming classes. Thank you very much.